Hello everybody, welcome back to the Master Answer 1 course. So we already have discussed some important topics in the first five sessions. So let us now move on to the session number 6. So before we start the discussion, let us just say what we learned in the previous session. In the previous session, we took up a topic of the molecular diffusion in liquids. So under that, we derived an equation to estimate the rate of diffusion, that is Na, and in case of steady state diffusion of A through non-diffusing B, and also we uh, derived the equation for steady state equimolar counter diffusion. So we also solved a problem using the derived equations. So let us now see what we are supposed to learn next in the unit. So these are the contents that we are taking up in today's session. So we are going to discuss what is meant by a mass transfer coefficient. So then the relation between the individual mass transfer coefficients called the film coefficients, and also the relationship between the overall and the individual mass transfer coefficients. See, so far we've been deriving the rate equations for the diffusion that takes place in the individual phases, that is for molecular diffusion. So let us, if we consider that a turbulent diffusion, so which is usually case in the various mass transfer operations, then the flux equations are usually written in terms of mass transfer coefficients. So in a turbulent diffusion, there are three regions over which the mass transfer occurs. So one is the turbulent region, other one is the transition region, other one is the laminar region through which the diffusion occurs by molecular diffusion. So as it is very difficult to know the distance through which the that is a turbulent region through which the diffusion occurs, um, we can consider that the entire resistance to mass transfer lies in the laminar sublayer of thickness Z. So this laminar sublayer thickness is called as effective laminar film thickness. So what I'm trying to say is all the diffusion equations, that is molecular diffusion rate equations that we have derived for molecular diffusion, can therefore be used for turbulent diffusion case also. So just substituting the distance over which the diffusion occurs, that is a z term in the equation, by substituting that z with the thickness of effective laminar sublayer. So that is how we can write the equations for the rate of mass transfer that usually takes place with a turbulent motion. So in that case, the flux equation can be written as flux is equal to mass transfer coefficient into concentration difference. So according to this equation, we can now define the mass transfer coefficient as the rate of mass transfer per unit area per unit concentration difference. That is, the number of moles of diffusing substance that diffuses per unit time per unit area per unit concentration difference is what is known as the mass transfer coefficient. Okay, let us recall all the equations derived for various cases of diffusion in gases and liquids. So under gases, under steady state diffusion of A through non-diffusing B, we derived two equations, one in terms of partial pressure concentration terms, another in terms of mole fractions. So Na is equal to dABP by RTZ ppm into Pa1 minus Pa2 is one such equation. So in terms of mole fraction, the same equation becomes Na is equal to dAB by RTZ YBm Ya1 minus Ya2. So there is another equation for the same case. Na is equal to dAB P square by RTZ PBm into Ya1 minus Ya2. So in the same way, for the other cases of diffusion, that is steady state equimolar diffusion in gases, and the two cases of diffusion in liquids also, we derived the various equations as I have listed in the given slide. Now, so in all these above rate equations, the term Z can be written as ZL or ZG. So for example, if you take the first equation dAbP by RTZ ppm, here the Z represents the distance over which the molecular diffusion occurs. So if the same term is replaced by Zg, because Zg we are using because we are using the partial pressure as the concentration terms, and this is a equation that is written for the gas phase. Okay, so the Z becomes Zg in this one, where that Zg, Z suffix G, is the effective laminar film thickness, means the laminar sublayer over which the entire resistance to mass transfer lies. So that equation then can be used for writing down the flux equation for the mass transfer taking place between the phases, that is taking place in turbulent condition. So then the equation becomes rate is equal to coefficient into concentration difference. So if you again take the first equation, Na represents the rate, then the whole term dAbP by RTZG ppm represents the coefficient, and Pa1 minus Pa2 represents the concentration difference. So if you take the second equation, then Na is equal to dAbP by RTZG again in the denominator, so Ybm into Ya1 minus Ya2. So in this case, the coefficient is represented by dAbP by RTZG Ybm, and the concentration difference is in the form of Ya1 minus Ya2. So in the same way, we can go on writing the flux equations for various cases of diffusion in turbulent region. So in all these cases, Na becomes the mass transfer rate, then all the constant terms along with the Zg or Zl in the denominator becomes the coefficient, and whatever that is there inside the bracket that is involved, that contains the concentration terms between the initial and the final location gives the concentration gradient. Now we can write the equation in terms of rate is equal to coefficient into concentration gradient. So all these group of constant represents the various types of coefficients in each cases of diffusion in a turbulent region. So let us now write down those equations in short form like this. So Na is equal to dAbP by RTZ ppm will become Na is equal to small k suffix g Pa1 minus Pa2. So Kg here is a individual mass transfer coefficient for gas phase. In the same way, for the same case, we have Na is equal to dAbP by RTZ by Bm into Ya1 minus Ya2. So that dAbP by RTZ by Bm can be now written in a short form in a single term called Ky, so which represents the individual mass transfer coefficient with respect to gas phase. So similarly, Na is equal to Kc into Ce1 minus Ce2 for the same case. So in the same way, if you go on writing the equations for different cases, so these are the set of equations for each cases of diffusion. So the first three equations represent for gases in case of steady state diffusion of A through non-diffusing B. The second two equations for the same case of diffusion in liquids. So similarly, for the other two set of equations at the bottom are written for the equimolar counter diffusion in gases and liquids respectively. So like this, if you look at all these equations, you can see that there are a variety of individual coefficients, all Kg, Ky, Kc, Kx, Kl, then Ky dash, Kg dash, Kx dash. So all these are called the film coefficients or individual mass transfer coefficients, because all these rate equations are written for an individual phase. That is, if you consider the mass transfer within a phase. So, for one case, if you take where the mass transfer is occurring from a gas phase to liquid phase, So Na equals kg into Pa1 minus Pa2, for example, represents the rate equation for the gas phase, and the Na is equal to Kx into Xa1 minus Xa2 represents the rate equation for the liquid phase. So under steady state conditions, both of these Na will be constant and they are equal. So the equation for the transfer of a component from a gas phase to liquid phase can be written as Na is equal to Kg into Pa1 minus Pa2 equals Kx into Xa1 minus Xa2 or equals Kl into Ca1 minus Ca2 for this case of steady state diffusion of A through non-diffusing B. So in the same way, for the steady state equimolal counter diffusion, the flux equation under steady state conditions for a transfer of a component from one phase to another can be written as Na is equal to Kg dash Pa1 minus Pa2 equals Kl dash Ca1 minus Ca2. The rate of transfer of component from within one phase will be equal to the rate in the other phase. So that is the situation what you have in a steady state condition. So using these equations, let us now write down another um, rate equation that can be written in terms of overall coefficients. So if small kg, small ky represent individual coefficients, then capital Kg and capital Ky, capital Kx, and all such terms can be used to represent the overall coefficients. Okay, so before we take up the overall coefficients, let us just understand there exists a relationship between all the individual mass transfer coefficients. So this is the coefficient, the relationship that is existing between the various coefficients for gases and for liquids. So in case of gases, the relationship is like this: Kc dash into P divided by RT is equal to Kc dash into C. That equals Kc ppm by RT, that equals Kg dash P, that equals Ky dash, that equals Ky Ybm, that equals Kg ppm, that equals Kg into Ybm into P. So this is the relationship that exists between the various individual film coefficients for gas phase, and the same way we have a relationship in case of liquids as well. So KL dash will be equal to KL dash into rho by m average, that equals Kx dash, that equals Kx xbm, that equals KL xbm into C. So that is all about the relationship between the mass transfer coefficients. Now let us understand the overall mass transfer coefficients. The mass transfer film coefficients are difficult to measure except for cases when the concentration difference across one phase is small and thus can be neglected. So in all such cases, the overall mass transfer coefficients are measured on the basis of the gas phase or the liquid phase driving force. So that is what is meant by overall coefficients, overall mass transfer coefficients. So now we can write the flux equations considering the overall concentration difference across both the phases, but the coefficients are written based on either the gas phase driving force or the liquid phase driving force. So for that purpose, if you write the overall rate equation for steady state diffusion of A through non-diffusing B, the equation becomes Na is equal to capital Kg Pa minus Pa star. See, Pa is the concentration of A at the starting point from where the diffusion actually occurs, that is transfer actually occurs. So then that concentration Pa so will gets reduced to PAI at the interface between the phases. Then from PAI, it drops to some liquid phase concentration, say Ca. So we cannot write the equation as Kg into Pa minus Ca because since the Kg coefficient is based on the gas phase mass transfer resistance, then there should be written or the second concentration term should be again written in terms of the gas phase concentration terms, that is in terms of PA only. So instead of writing Ca or Xa, so we can write one term called Pa star. So that is the concentration of A in gas phase that is in equilibrium with the liquid phase concentration at which the uh, diffusion ends. Okay. So now let us write down the individual the flux equation in terms of individual coefficients for the same case and try to get a relationship between this overall coefficient and the individual coefficients. For the given case of steady state diffusion of A through non-diffusing B, the flux equations including the individual coefficients will be like this: Na is equal to Kg into Pa minus Pai. So this equation gives you the rate at which the diffusion occurs within the gas phase from the gas phase bulk concentration to the interface concentration. So that is equal to again the rate at which the transfer takes place from the interface concentration in liquid phase to bulk liquid phase concentration. So that is equal to Kc into Cai minus Ca. So this equation clearly shows that the concentration is varying from Pa to Pai from the bulk of the gas phase to interface. Then in the same way, in the liquid phase, the concentration is varying from Cai, that is the interface concentration, to the bulk liquid phase concentration Ca. Now, the equation number 1 can also be written using the mole fraction terms like this. Na is equal to capital Ky into Ya minus Ya star. So Ya is the bulk gas phase concentration. So minus you cannot write Ca because the coefficient Ky is based on the gas phase. So instead of writing Ca, its corresponding equilibrium concentration Ya star has to be written. So in the same way, Na is equal to Kl into Ca star minus Ca. So Kl is a coefficient, overall coefficient based on liquid phase. So Ca star is the equilibrium concentration of A corresponding to the gas phase concentration Pa. So now using the first two equations, so let us arrive a relationship between the overall and individual coefficients. To get a relationship between the individual and overall coefficients, let us now expand the term Pa minus Pa star of equation 1. So we can write the Pa minus Pa star as Pa minus Pai plus Pai minus Pa star. So we are introducing the term Pai, that is by adding and subtracting the Pai to this term. So in order to get that individual coefficients into the overall coefficient equation. Now the left hand side Pa minus Pa star is nothing but Na divided by capital Kg. So that is obtained from equation number 1. Now on the right hand side, so we have Pa minus Pai, so which is nothing but Na divided by small kg, that is obtained from equation number 2. The third term in the equation, that is Pai minus Pa star. Here both Pai and Pa star are equilibrium concentrations. So because it's not that easy to find out the equilibrium concentrations, so its corresponding equilibrium concentration in liquid phase and gas phase have to be obtained. And that relationship between the equilibrium concentration is given by a law called Henry's law. So for example, Pa star is a equilibrium concentration. So that value is the concentration of A in equilibrium with the liquid phase concentration Ca. And the relationship between these two concentrations is obtained by the Henry's law, which states that the Pa star will be equal to H into Ca. So that H here is a Henry's constant. So in the same way, the relationship between Pai and Cai will be equal to Pai is equal to H into Cai. Okay. So in the same way, the relationship between Ca star and Pa, the equilibrium concentrations, is given by Pa is equal to H into Ca star. Now, substituting all these in the above equations and also the equation 1 and 2 in equation number 3. So we get this equation Pa minus Pa star is equal to Na divided by Kg, that is from equation 1. Then Pa minus Pai on the right hand side is nothing but Na divided by small kg, that is obtained from equation number 2. So the next term Pai minus Pa star in equation number 3. So instead of Pai, we can write HCai using Henry's law, and Pa star can be written as HCa again from the Henry's law. The H being a constant and common in both the terms can be taken outside the bracket. Then what you are left in that term is Cai minus Ca inside the bracket. Okay, now the Cai minus Ca from equation number 2 is nothing but Na divided by small kl. So the equation becomes Na divided by capital Kg equals Na divided by small kg plus H into Na divided by small kl. So here Na being common on both the sides gets cancelled, and you get a final equation, that is 1 by kg, that is capital Kg, will be equal to 1 by small kg plus H divided by small kl. So this is the relationship between the overall coefficient capital Kg and the individual mass transfer coefficients small kg and small kl. So in the same way, if you go on deriving, you can get the relationship between all the other overall and individual coefficients. So we can expand the Ca star minus Ca, that is written in the second equation as Ca star minus Cai plus Cai minus Ca. So here also Ca star and Cai are the equilibrium concentrations which can be related to Pa and Pai by using Henry's law. So Ca star is equal to Pa divided by H. So then Cai is equal to Pai divided by H. Then the left hand side Ca star minus Ca is nothing but 1 by KL or Na divided by KL from equation number 1. This equation number 2. So and also the Cai minus Ca in the right hand side is nothing but 1 by small kl. So the middle term Pa minus Pai is 1 by small kg. So the equation becomes 1 by capital KL equals 1 by H into small kg plus 1 by small kl. So this is another kind of relationship between the overall coefficient KL, is capital KL, in terms of individual coefficient small kg and small kl. So that is how we can obtain the relationship between the overall and the individual mass transfer coefficients. Okay, so this is a recap of the today's class. Mass transfer coefficients, relation between the film coefficients, and the relationship between the individual and the overall mass transfer coefficients. So with that, we have ended the present session. So let us again meet in the next session for the discussion on the other topics.